This is Unit 7, Electrons, Part 2 Notes. By the end of this unit, you should be able to express the arrangement of electrons in atoms and ions based on electron configurations and electron orbitals. So whenever we were analyzing the atomic structure and how it changed over time, we ended with the Bohr model that described the path of electrons around the nucleus based on energy levels. So he took Rutherford's depiction of the atom and he organized the electrons on energy levels so it looked like something to the right. And then I told you the next person, Schrödinger, came in and used quantum mechanics to determine those energies where electrons are most likely to be found, but we didn't have to know him at that time. Well, now we need to know that because Schrödinger came in later and used this quantum mechanical model that determined the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus of the atom. So even though electrons are traveling on different energy levels, they are in more specific orbitals that we need to discuss and analyze because they don't just travel on the same level. They actually have different types of orbitals that we need to investigate. So Schrödinger proved the Bohr model to be not as accurate as it should be. So Schrödinger later defined the atomic orbitals representing the probability of finding an electron and are represented pictorially as a region of space. So there's four different types. There's four major ones. We have S, P, D, and F. The S shape is your spherical shaped. The P, there's three different types of P's. They're on the X, Y, Z axis. And they look like dumbbells. They look like lobes. And then your D or dumbbell shaped type orbitals, there's about 5 of them. And then the F is a flower shaped type orbital. And these are more specific to the energy levels that we can locate the electrons on. And we will be discussing these orbitals in detail. So your principal quantum number can represent the atomic orbital size and principal energy level. And the trend is electrons in larger orbitals are further away from the nucleus, and they have more energy. So if you have valence electrons, the further away they are from the nucleus, the less interaction they have with that positively charged nucleus, allowing for that reactivity to happen. So the general trend is the further you away are from the nucleus, the more energy that you have. And your principal energy levels can then be divided into sublevels or subshells that have your SPDF orbital type within them. So on your first energy level or your principal energy level, you can only have an s orbital, hence that first ring can only hold 2 electrons. That is your first energy level. And then we end up going to our second energy level, and then that can contain s and p type orbitals holding a maximum of 8 electrons. Then we can go into the third energy level with our s, p, and d type sublevels holding a maximum of 18 electrons. And then our fourth energy level can have S, P, D, or F orbitals that contains a maximum of 32. And if you look at the periodic table in my classroom, the next time you come into the class, if you look at the side, there's the 2, 8, 18, 32 trends going on, and that's what they're talking about, the types of orbitals and the maximum number of electrons. Okay, so this slide is going to be one of your extremely important slides to have everything in here written down and drawn out, especially the sublevels to your right. But the sublevels, S, P, D, and F, we need to know the number of orbitals that they can have and the maximum number of electrons. So your S sublevel has only 1 orbital, and that can hold a maximum of 2 electrons. So think as the boxes represent an orbital, and 2 electrons can fit inside of that box, or in each of those boxes. Okay, so, or you can say 1 times 2, you can have 2 electrons. In your P level, that's a little bit further away from the nucleus, and those have 3 orbitals, and since each orbital can have 2 electrons, that's where you get the 3 times 2 is 6 maximum electrons. Then you have your D orbital. There's 5, 1, 2, 3, 4, 5 orbitals, a little bit further away from the nucleus, and each of those can hold 2 electrons. That's why you get a total of 10. And then your F has 7 orbitals here. That's a little bit further away from the nucleus as well. And each can hold 2 electrons, hence you have the 14 total electrons in your F sublevel. So if you notice, I mentioned that each orbital, as you go from S, P to D to F, you increase in the amount of energy because they're further away from the nucleus. S is the closest, then P, then D, and F is the furthest away. And we can fill these orbitals based on 3 rules. And these 3 rules you need to know and to memorize. Your off-bow principle tells you that electrons occupy orbitals in the lowest energy first. So we need to always start with our S sublevel. That's what that means. The Pauli exclusion is in an atomic orbital, only holds 2 electrons at most. And if you have 2 in the same orbital, they need to have the opposite spin. So if I'm trying to fill in my S sublevel, I have 1 electron pointing up and then 1 electron going down. So we represent electrons by using our arrows. So one goes up and one goes down, representing the opposite spin so they can fit in close together. Then our Hun rule says that when you fill orbitals that have more than 1 orbital, hence your P, D, and F, you have to fill the electrons in singly before you match them up with the opposite spin. Just like in your Lewis dot structures, whenever you're adding in dots per side, you have to fill it up singly before you can go back up and pair. So in my P, let's say I'm trying to fill in my P orbital, and I have 4 total electrons. I want to fill in single up, single up, single up. They all have to be in the same direction before I can go back in and pair them up together with the opposite spin. If your element had 5 electrons in the P level, you could fill arrow down or even add another one if it had 6 electrons in the P sublevel down. But again, for your Hun's rule, you have to fill in all the orbitals singly in the same direction first before you can go back up and pair the electron with the opposite spin. Okay, so if you're ever needing to draw atomic orbitals, I'm going to show you a couple of examples first. So let's practice with lithium. Lithium is element number 3, so it's going to have 3 protons and 3 electrons. We're assuming everything is neutral. Okay, and as you go from left to right, you're increasing energy, so we always have to fill up the first sublevel first before we can go on to the second sublevel. Okay, so lithium has 3 electrons, so I'm going to fill in my 1s orbital first with 2 electrons. So I'm using off-Bell's principle, filling the least amount of energy first. I'm using the Pauli exclusion principle, where they're paired together with opposite spins. And I don't need to use Hun rules yet because I'm not in the P, D, or F orbital. So now that I have 2 electrons, I go back in and fill in my last electron to represent your 3 electrons. So all your arrows are going to be represented or represent each single electron. So then going into fluorine, fluorine is element number 9, so I need 9 electrons. So again, going from left to right, you're increasing in energy. So we have to fill in our 1s level first with 2 electrons. So there's 1 electron, 2 electrons. Then I need to fill in my 2s because it has a little bit more energy with 1 electron, 2 electrons. So now I have a total of 4, and I need to get to 9. So I need to place 5 electrons in my p orbital. So using Hun's rule now, I have to fill in my electrons singly. So now I'm at 5, 6, 7. I need to fill in 2 more, so I place them down. And this would be the atomic orbitals for both lithium and fluorine. And then we can represent these atomic orbitals into what is known as electron configurations, which we're going to define on the next slide. But how you would relate the two together, my 1s orbital has 2 electrons, my 2s orbital has 2 electrons, and then my 2p orbital has 5 electrons. Going back to lithium, my 1s orbital has 2 electrons, and then my 2s orbital has 1 electrons. So we can interchange between the orbital diagram versus the electron configuration. So electron configurations are just describing the way electrons are arranged in various orbitals around the nucleus of atoms. The lower the energy, the more stable the atom is. A ground state electron configuration is just describing the way electrons are arranged in various orbitals around the nucleus with the least possible energy. There are higher state type electron configurations, which we will discuss whenever bonding comes around, but ground state electron configurations is where you have the least possible energy. I handed you guys out a periodic table handout that needs to be glued in where you write these notes, because that helps you identify the order of your atomic orbitals. And you have to memorize the increasing order based on the S, P, and D and F block. So we talked about the sphere, dumbbell, and lobe-shaped orbitals. Your 1s or your S block is going to be with groups 1 and 2. You also need to know that your P block is groups 3A through 8A. Then you have your D group, which is your transition metals. And then your F block, that is your lanthanide and actinides. So we have to know the SPDF and where they are located. But whenever you're writing electron configurations, we have to base it off of, first, the off-bow principle, where we have to fill in from the least amount of energy first. And you always start with the 1s block, because the first energy level always has the least amount of energy as compared to the 7th, and your S has less energy than your P, then your D has a little bit more, and then your F has the most amount of energy. So we all base it on the electron number. Hydrogen is element number 1, so I'm only going to have 1 electron in my orbital. So in your 1s block, you have 1 electron. The exponent is going to tell you the number, or the total number of electrons. If you go to helium, which is element number 2, you're going to have 2 electrons in your 1s orbital. Carbon is element number 6, so I have to first fill up my 1s with 2 electrons, because that's the maximum number of electrons. Then I go on to my 2s, fill that with 2 electrons. Now I have 2 plus 2 is 4. Now I go on to my 2p, and I fill up my 2p with 2 electrons, because now I have 2, 4, 6 electrons in my electron configuration. Sodium is a little bit longer, so I'm going to write sodium down here at the bottom. Sodium is element number 11, so I have to first start with the 1s orbital. I fill up my, that's the number of atomic number 11. I fill up my 1s orbital with 2 electrons. Then I have to fill up my 2s orbital with 2 electrons. Then I fill in my 2p orbital with 6 electrons, so now I have 6, 7, 8, 9, 10 electrons, and I need 1 more, so then I fill in my 3s with 1 electron. Hence, I have a total of 11 electrons in my electron configuration. So this is just explaining where the electrons are located, what energy level, and what orbital type we can locate them in, and this is all based on the Schrodinger quantum mechanical model. Okay, so there's 2 other ways to write these electron configurations. We have our noble gas. This is a shorthand notation where we use the noble gas in the previous row within brackets. Brackets look like this, and then that's going to contain the amount of electrons according to the atomic number. And then we continue on from where we're at on the periodic table within the electron orbitals. So for example, boron. This is element number 5, and it's on period number 2 on the periodic table. If it's on row 2, I have to use the noble gas on the previous period, which is period number 1, and I write helium within brackets. This helium's atomic number is 2, so I have contained 2 electrons within that electron configuration, and then now I need to add 3 more electrons to complete my total electron configuration. So I ended at the 1s2 block, so then I continue on with my 2s2 and then my 2p1. Now I have 2 electrons within the brackets, plus 2 is 4, plus this 1 would be 5 total electrons, hence this is the shorthanded notation of boron. Sodium, the previous slide, we wrote out the entire electron configuration. It's on period number 3, so I have to use the noble gas in period number 2, which is neon. The atomic number of neon is 10, so I have 10 total electrons within the bracket. Then I continue on with my 3s1 notation to have a total of 11 electrons within my configuration. So this would be the shorthanded notation versus the previous one we just wrote down. In ion electron configurations, we either add in or just take away those electrons. So for example, beryllium is element number 4. So beryllium atom would have 1s2 and then 2s2 configuration. But beryllium is in group number 2, and it forms a +2 charge. That means it's lost 2 electrons. So it's just going to lose those 2 in the outer valence shell. So its ion configuration would just be 1s2, which is the exact same configuration as helium, which makes sense. They're going to mimic a noble gas. Nitrogen is element number 7. So using our electron configuration, I'm going to fill in my 1s2, then my 2s2, and then my 2p3 to get a total of 7 electrons. But neon forms a -3 charge. How do I show adding in 3 electrons? You add them into the valence shell. So this 3 here is going to turn into a 6. So its ion electron configuration would be 1s2, 2s2, 2p6. And this is exactly the same as the neon electron configuration, so it's mimicking noble gases. Hence, your ions form charges based on the noble gas that they want to mimic. And then aluminum is element number 13. Okay, so this is a 1s2, then I fill in my 2s2, then I fill in my 2p6, and then you go to your 3s2, and then you fill in your last one with a 3p1. So you should add up the exponents. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. But aluminum forms a +3 charge, so it's going to lose 3 electrons in the outermost ring. So in your row 3, or your third energy level, I have 3 electrons that are going to be lost. So the ion configuration for aluminum would be 1s2, 2s2, 2p6, because it's also going to mimic the noble gas neon. Okay, so have you accomplished the objectives? Are you able to write the arrangement of electrons of atoms and ions based on electron configuration and electron orbitals? If not, that is okay, because we will spend time in class going over this lecture, making sure a little bit more information is understood from it. Just make sure you have these notes written down before you come to class the day that we are going to have this lecture.